You know that phrase you sometimes hear? The climate has always changed.
Oh, yeah, definitely. It comes up a lot.
Right. And it's often used like, well, that settles it. Nothing to worry about now.
Hmm.
So, okay, let's actually dig into that idea properly. Today, we're doing a deep dive into exactly that sentiment. Is what's happening now just, another chapter in Earth's long climate story? Or is it something else, something more urgent?
And we've got two really interesting sources to look at here. They seem to offer, well, pretty different perspectives on this whole thing.
Exactly. First, there's an article called How Did We Get Here?
Yeah.
By Guy DeWhitney. It takes this huge, multi-billion-year view.
That's right. And then we have Epochs, Urgency and Understanding by Daniel Sanderson. This one seems to directly respond to those kinds of long-term arguments, really focusing on the speed of the changes we're seeing right now.
Okay, so our mission here for this deep dive is to try and get a much clearer picture of what these different viewpoints actually mean. Are the shifts we're experiencing now just, business as usual for the planet over the really long haul?
Or is there something fundamentally different about what's happening today, especially, like you said, when we think about how fast it's all unfolding?
Yeah, the pace. It seems key.
It really is. It's not just about saying, oh, yeah, climate changed before. I mean, the geological record is crystal clear. It absolutely did.
No question there.
But it's about understanding how those past changes stack up against what's happening now. The speed, the drivers, and what that actually means for life today, for us.
Okay, let's start with the Whitney's article then. How did we get here? This one really takes the long view, doesn't it? Starts way back, formation of stars, planets, brings us right up to today. What's his main point about climate change when you look at it through that massive lens?
Well, DeWhitney's whole perspective is anchored in that huge geological timescale. He points out that Earth's climate has swung wildly in the past. We're talking periods with massively higher CO2 levels than now.
Right.
So his main takeaway is that, viewed against that backdrop, the current changes, they don't look particularly unusual. He even kind of suggests they might be a good thing, maybe, especially for plants, if you look at that history.
He talks about these natural processes, too, right? Things pulling CO2 out of the air over millions and millions of years, like sedimentary rocks forming.
Exactly. Think of layers building up over eons, trapping carbon. He also mentions CO2 reacting with minerals, calcium and magnesium oxides, forming stable carbonates, basically carbon getting locked away in rocks.
So he's painting a picture of the planet being on this very, very long-term trend of CO2 decreasing in the atmosphere.
That's a good way to summarize it, yeah. He argues that over these vast geological stretches, CO2 has been steadily removed and stored in the Earth's crust. He says, CO2 is slightly acidic, reacts with alkaline minerals, forms these stable compounds.
And volcanic activity puts them back, but not enough to reverse the overall trend.
That's his point. He suggests that volcanism hasn't kept pace with the removal processes over the grand sweep of time, so a long-term decline.
Which leads him to talk about those ancient periods with super high CO2. He says Earth was warmer, wetter, and calls them the very best times for life. That's quite a statement.
It is a strong statement. Of course, life back then was very different. We're talking about conditions that, modern ecosystems, including us, aren't adapted to at all.
Good point. So when he says current CO2 levels, around 0.04%, are low historically.
Yeah, he frames it as being near the lowest levels in Earth's history and actually approaching what he calls a dangerous level for plants, around 0.02%.
So his concern isn't too much CO2, it's potentially too little in the long run.
That's the implication. From his perspective, the recent increase from human activities isn't the worry. It might even be counteracting that long-term decline. A good thing, maybe.
Potentially revitalizing the biosphere, he suggests, preventing a future CO2 shortage for plants.
That's his interpretation, yes. He essentially proposes that human emissions are just starting to nudge things back up, potentially benefiting plant life.
And he goes further, doesn't he? Saying the politically driven global warming fad lacks solid science.
He does use that phrasing, yes, and suggests the CO2 we're adding could be a net positive for life on Earth.
And importantly, he adds a note saying his article is based on completely uncontested facts, taught in science and checked by experts. That sounds very definitive.
It certainly projects confidence, but this is precisely where Daniel Sanderson's article, Epochs, Urgency and Understanding, provides a crucial counterpoint.
Okay.
Sanderson doesn't really argue with the basic facts of Earth's climate history. Yes, CO2 was higher way back when. That's not the dispute.
So what is Sanderson's focus?
The rate. The speed of change. That's the absolute core of his argument. He says the speed at which CO2 is rising now, driven by us, by human activity, makes those comparisons to the deep past potentially quite misleading. And that is the reason for the urgency.
Oh, okay. So it's not just about the level of CO2 we might reach, but how blindingly fast we're getting there compared to past changes.
Exactly. He draws this really sharp contrast. You have the slow, gradual climate shifts over millions of years in the geological past.
Right, driven by natural forces.
Versus the incredibly rapid changes happening now on the scale of decades, not millennia or eons.
Sanderson does mention those past CO2 levels, like 4,000 parts per million in the Cambrian, 2,000 in the Devonian, and then the Ice Age is down at 180 ppm. But he uses these to highlight the speed difference, right?
Precisely. He explains those past changes were driven by things like huge long-term volcanic outgassing, or the slow burial of carbon in rocks and sediments, the evolution of land plants sucking up CO2, even the sun's output changing over billions of years.
And he notes the sun was fainter back then, too, which is important context.
A really crucial point, yeah. You can't just compare CO2 numbers directly without considering that the sun was giving off less energy in the distant past.
Okay, then he zooms in a bit, looking at the last 800,000 years or so, those natural ice age cycles. CO2 going between roughly 180 and 280 ppm. What's the key lesson there?
The key lesson is, again, the speed, or lack thereof, relatively speaking. CO2 levels rose by about 100 ppm, coming out of an ice age, sure, but that rise to thousands, sometimes tens of thousands of years.
It's so very slow climb.
Very slow. We're talking maybe 0.005 to 0.01 ppm increase per year, on average, during those natural warming periods.
Okay, and now contrast that with what's happened since the Industrial Revolution. The numbers Sanderson gives are pretty stark.
They really are. Pre-industrial levels were stable around 280 ppm for a long time. Now, as of 2024, we're at 427 ppm. That's a jump of over 50%.
In just a couple of centuries.
Exactly. And look at the rate now. Since 1960, the average increase has been over 1.6 ppm per year. Some recent years, it's been over 2 ppm per year.
Wow. So compared to that natural post-ice age rate of 0.01 ppm per year.
It's orders of magnitude faster. Sanderson calculates the current human cause rate is roughly 250 times faster than the natural rate of increase coming out of the last ice age.
250 times faster.
Yeah, and he's very clear on the cause. Burning fossil fuels, cement production, deforestation. Our emissions dwarf natural sources like volcanoes. He says human emissions are at least 60 times greater.
And he mentions the Keeling curve, that graph showing the steady climb.
Right, as clear visual evidence of this incredibly rapid rise in atmospheric CO2.
So Sanderson's core message seems to be, look, our ecosystems, our agriculture, our cities, our whole human civilization we developed during the Holocene, the last 11,700 years or so, which is a period of unusual climate stability.
Relatively stable.
And this incredibly rapid change we're forcing now, it's like a massive shock to that system. It's happening too fast for natural systems, and even for us, to adapt smoothly. It's not a gentle nudge.
It's a shove, a sudden, forceful shove. That's a good way to put it. And he points to the overwhelming scientific consensus, citing the IPCC, the Intergovernmental Panel on Climate Change.
Right, the IPCC findings.
Which state it's extremely likely that most of the warming since the mid-20th century is human-caused. Their best estimate is actually that humans are responsible for about 110% of the observed warming, meaning other factors might have even caused slight cooling.
Okay, and then Sanderson lays out the consequences of this rapid change. It's not just about temperature, is it?
Not at all. It's a whole cascade of effects. He mentions ocean acidification. The ocean soaking up CO2 makes the water more acidic.
Which is bad for things with shells.
Exactly.
Yeah.
Corals, shellfish, plankton, the base of many marine food webs. And this acidification is happening about 10 times faster than anything seen in the last 55 million years.
10 times faster.
Then there's sea level rise. It's accelerating, rising faster now than at any time in at least 3,000 years, directly threatening coastal areas.
And extreme weather.
Yes. More frequent and intense heat waves, heavier downpours causing flooding in some places, deeper droughts in others, potentially stronger storms. The fingerprints of climate change are increasingly visible in extreme events.
And the impact on biodiversity, on other species, sounds really serious too.
It really does. Sanderson highlights that current extinction rates are estimated to be up to 1,000 times higher than natural background rates. Climate change is a major driver affecting thousands of species.
He mentioned climate velocity. What's that?
It's basically how fast temperature zones are shifting across the landscape or through the oceans. Species have to try and keep up, migrate, adapt, or face decline. If the velocity is too high, they just can't keep pace.
Which leads to biodiversity loss. And he also mentioned food security threats, human health risks.
Yeah, impacts on fisheries, crop yields, heat stress, the spread of diseases carried by insects, respiratory problems from air pollution often linked to fossil fuels, malnutrition, even mental health impacts from dealing with disasters or environmental change. It's very wide-ranging.
Okay, but what about DeWhitney's point about CO2 being plant food? That sounds beneficial on the surface. How does Sanderson counter that?
Sanderson acknowledges that plants need CO2, obviously, but he explains the issue isn't just having CO2, it's the rapid surplus that's destabilizing ecosystems adapted to lower levels.
Hmm.
Plus, it's not universally good for all plants. Some major crops, C4 plants like corn, might actually be at a disadvantage relative to weeds, for example, at very high CO2 levels. The rapid change itself is the problem, overwhelming any potential benefits for many systems.
So Sanderson really pulls the focus back to the timescale that matters for us right now. Human civilization, current ecosystems. He's saying, sure, Earth saw high CO2 millions of years ago.
But the conditions were totally different. The sun was dimmer, life was different, the continents weren't even in the same places. He argues those deep past comparisons aren't very relevant for understanding the risks we face now.
He does bring up a slightly more recent period, the Pliocene, a few million years ago.
Yes, as a potentially more relevant, though still imperfect, comparison, back then CO2 was around 400 ppm, similar to today. And guess what? Global temperatures were significantly higher, sea levels were much higher, maybe 10, 20 meters higher than today.
Wow. Okay, so that gives a hint of where sustained levels like today's might lead.
It serves as a paleoclimate analog, yeah. And Sanderson keeps coming back to the Holocene, that period of relative stability for the last, say, 12,000 years. That stability, he stresses, is what allowed agriculture, settlements, complex societies, basically, human civilization as we know it, to develop and flourish.
So if we try to synthesize these two views, DeWitney and Sanderson, the core disagreement isn't really about the facts of past climate change. Both acknowledge it happened.
No, the facts of the past aren't really in dispute. The divergence is all about the interpretation and the significance of the current changes, specifically the rate.
DeWitney looks at the immense timescale, sees higher CO2 levels in the deep past, and concludes the current situation isn't necessarily alarming, maybe even beneficial.
Right. He emphasizes the long-term context.
Sanderson looks at the speed of the current increase, compares it to past rates of change, especially in more recent geological history, sees it's unprecedentedly fast, human-caused, and highlights the risks this poses to systems adapted to Holocene stability.
Precisely. He emphasizes the rate and its implications for adaptation for both ecosystems and human society. He mentions things like the evolution of different types of photosynthesis, C3 and C4, as examples of how life adapts slowly over eons, something that just can't happen on the scale of decades or centuries.
And just to be clear, in looking at these two articles, we're not taking sides or endorsing any political stance here. Our goal is just to understand the arguments being presented based on the science they discuss.
Exactly. Both sources use factual information, but they frame it very differently. One uses the lens of deep geological time. The other uses the lens of timescales relevant to current life and civilization. And it's fair to say that the overwhelming scientific consensus, as reflected in Sanderson's piece and the vast body of climate science research, supports the view that the rate of current change is the critical issue and poses significant risks.
Okay, so the big takeaway from this deep dive really seems to crystallize around that point. Yes, Earth's climate has always changed, sometimes dramatically. No one disputes that. But the speed at which human activities are changing it now is what makes this current period fundamentally different from those past shifts, certainly within the timescale relevant to human civilization and current ecosystems.
That's the crux of it. The speed is overwhelming natural and societal adaptive capacities. It's the rate of change that signals urgency.
Which leaves us with a final thought for you, the listener, to chew on. When you consider that vast, almost unimaginable timescale of Earth's history, billions of years, and then you think about the incredibly short time human civilization has really existed.
It's a blink of an eye, geologically speaking.
Right. What does this incredibly rapid human-driven shift happening right now actually signify about our power, our impact, our place on this planet's long-term path?
And what responsibility comes with understanding this difference, knowing that the changes we're causing are happening hundreds of times faster than the natural cycles our world adapted to?
Yeah. What responsibility does that understanding confer upon us? Definitely something to think about.